Okay, welcome to Geometry, Chapter 9, Section 4, Compositions of Transformations. Pause the video and then come back and I will just reveal the key for you. So make sure you have your answers ready. And number 1 should be at 1, -6. Number 2, 7, 4. Remember it's opposite y, x, right? And a reflection across the y-axis leaves you with -4, -7, so the x is the opposite. So today we're going to apply theorems about isometries and identify and draw compositions of transformations such as glide reflections, compositions, more than one. Vocab includes composition of transformations and a glide reflection. So what is one transformation followed by another? Yes, a composition of transformations. For example, a glide reflection is the composition of a translation, that's the glide part, and a reflection across a line parallel to the translation vector. Okay? So a glide reflection that maps JKL to JKL prime is the composition of a translation along vector V followed by a reflection across line L. So first a translation along the vector V and then boom, a reflection across line L. The image after each transformation is congruent to the previous image. So by the transitive property of congruency, the final image is congruent to the pre-image. So this leads to this theorem. A composition of two isometries is an isometry. So a translation and a reflection are isometric transformations, right? When we translate, the image is congruent to the pre-image, right? Just moved it, in this case, to the right, positive in the horizontal direction, right? And then the reflection across line L leaves us with a congruent triangle as well. These are congruent, the pre-image and the image. And so this composition transformation is an isometry. If you have two isometries, you get a total isometry, right? So how does one draw compositions of isometries? We draw the result of the composition of isometries, just as we saw in that previous glide reflection. So reflect PQRS across line M and then translate it along vector V. So the first step would be to reflect PQRS across the given line M. Remember that each vertex is the same perpendicular distance from this line of reflection, right? And then the second thing would be to translate this reflected image along the vector V to find the final image, PQRS double prime. Okay? Let's see if we can draw the result of the composition of isometries in a coordinate plane. So we have KLM with the given vertices, you can see here, and we're asked to rotate it 180 degrees about the origin, 0, 0, and then reflect it across the y-axis. Okay, so why don't you do the math behind a rotation of 180 degrees? You remember what that math is? That's right. It is, for a 180 degree rotation, just take the negative x and the negative y. So we can go ahead and complete the math for the coordinates, and we have those given coordinates, right? So our image of the original can be plotted, so go ahead and plot it, and we have that in the green here. Okay, so there's your 180 degree rotation. Now we're going to reflect that image, and we were asked to reflect it in the y-axis. So which value here is changed to the opposite? And that would be the x, right? When we are reflecting in the y-axis, we change to the opposite x. So we go ahead and fill those coordinates in. There you go. And we have the ability to plot them. And here is our final image. I put a box here just to make it a little trickier for you in case a person thought that a reflection in the y-axis leads you down here, and it does not. This would be a reflection of the green over the x-axis, right? An interesting composition is one of two reflections across two parallel lines. When we do a double reflection across two parallel lines, we get a transformation that is equivalent to a translation. Notice we have a reflection across the first line. See, the vertices are the same distance from this line on either side of the line, right? And then if we reflect across the second line, notice the distance is greater from, let's say, this vertex to the line. But when we go that equivalent distance, we have this image, right? The length of the translation vector is twice the distance between these two lines. Isn't that interesting? So this vector is twice the distance between the parallel lines. The composition of two reflections across two intersecting lines is equivalent to a rotation. So this is kind of interesting. We reflect the red triangle to the green and the green to the blue, and notice we end up with a rotation. The center of rotation is the intersection of the lines, this point here, the point of intersection. The angle of rotation is twice the measure of the angle formed by the line. So here's the lines. We have an angle here, let's say it's 40. Then the angle of rotation between this first image and the final image would be 80, double the measure of the angle formed by the intersecting lines. So here we have an art application. Sean reflects a design across line P and then reflects the image across line Q. Describe a single transformation that moves the design from the original position to the final position. And what would you call that transformation? That's right, a translation, right? And here we can see the final image over here. The composition of two reflections across parallel lines is equivalent to a translation, perpendicular to the lines. So the vector, if we have a distance of 5 centimeters between the parallel lines, then the vector would be 10 centimeters long, twice the distance between the parallel lines. This theorem is kind of the converse of what we were just talking about. A translation, or any rotation, is equivalent to the composition of two reflections, right? A translation would be two reflections across parallel lines. A rotation would be the composition of two reflections across intersecting lines. Let's describe transformations in terms of reflections. So you have this image in your notes, and we can see that two lines of reflection can be drawn that produce an equivalent transformation. So if you were given these figures, could you draw the two lines that would result in the final transformation? What you don't see here is the first reflection of the blue triangle, and what you do see is the combination of two reflections, right? Pause the video and attempt to draw two lines of reflection that produce an equivalent transformation. Come back and check your work. Okay, so we would have in this case a rotation. So these would be looking something like this, right? We would have a reflection and then a second reflection, right? And we can draw the angle bisector PX and the bisectors APX and A prime PX. To draw the perpendicular bisector of a segment, we can use a ruler to locate the midpoint, and then we can use a right angle to draw a perpendicular line, right? Example 3. In this a figure has been shown to be translated from LMNP to LMNP prime. Notice the lines of reflection that produce this transformation, isometric transformation, right? So first M prime was drawn, and then a midpoint X was found on M prime, right? And then perpendicular bisectors were drawn of MX and M prime X. Those perpendicular bisectors are the lines of reflection, right? So the distance between them, these parallel lines, are half the distance of the entire M to M prime. And that makes sense, right? Because they travel between the two midpoints. So, okay, pause the video, come back and check your work. Number 1, number 2, these are the coordinates you should have found. And drawing your lines of reflection, you should have drawn a segment between two corresponding points, find the midpoint, and then a perpendicular bisector of each of those midpoints, right? Very good. And there you go.